Yeah, yeah,
And sum of the divisors, right?
yeah,
And for each prime factors, we split each one for one prime factor, right?
yeah.
This idea is also useful in uh, SUMaC. I think I told you a problem. It says unique factorization, something like that. It means that, for example, P1, P2, then we wanted to write it as product of primes. Remember that problem? For
Yeah,
example, 12, you can write it as 2 times 6, 3 times 4. It was bad because you can write it in two ways. And
yeah,
it's fine, all of them. In those problems, you should consider prime factorization and split into different parts, which each part is only related to one prime. So let's see here how it works. It's at the end denotes, the number of positive integers that divide n. So on the number of positive devices, right?
yeah,
For example, 12 is 2 squared times 3, 3 times 2, 6, right?
yeah,
It says f of n is dn over root n. So if you can say n1 is p1 alpha 1, p2 alpha 2, to pk alpha k, how can I write f of n?
um,
I want to split
oh,
different
alpha,
parts. That each part, first part only related to p1 alpha 1, second part p2 alpha 1. So
yes, it would be alpha 1 plus 1
over,
over um, p1 to the alpha 1 over 3.
yes, or cube root of p1 alpha 1, right?
Yeah,
Next one, alpha 2 cube root of p2 alpha. Alpha 3 plus 1 over cube root of p3 alpha 3. All the way to alpha k plus 1 over cube root of pk alpha k, right?
yeah,
It says there is a unique positive integer bn such that f of big N is greater than f of a small n for all positive integers. And that does not hold in it. Okay, what's the sum of the units of n? So we should find maximum, right?
yeah,
So as you can see, for example, for 2, for this one, each of them, this one is f of p1 alpha 1 times f of
yeah,
p2 alpha 2 times f of p3 alpha 3 to f of pk alpha 3. Then for each prime, we should find the maximum one. For example, look
yeah.
for 2, you say, okay, if you answer 2 to the 1, it would be what?
Um,
Over cube root of 2.
yeah,
If you answer 2 squared, it would be 3 over cube root of. So for example, for 2, you should find maximum is what? For 3, maximum is what? For 5, maximum is what? Probably after, for example, a prime number, it's better not to use them, right?
yeah.
And you can find. Want more hint or that's enough?
That's enough.
Okay.
Okay, I got an answer. I got E.
Okay, for power of 2, you've reached what?
2 cubed.
Okay, how we can prove that 2 cube is the best one?
Um, so you just check. So if you just compare them, and then
We can
using
we
2
can
cube roots.
change, take all of them into cube root, right?
Yeah, yeah.
So it is 4. This one is cube root of what?
Uh, that's cube root of 27 over 4.
Next one is cube root of what?
64 over 8. So just 8.
Yes, it is 4 over,
Cube root of 8.
which is 64 over 8, which is 8, right?
Yeah.
Okay. So This one is 6 point something. 2 to the 4 is 5 over cube root of 16, right?
Yeah. So 125 over 16.
125 over 16.
A
How
little
we
less
can
than 8.
it is around, it's less than 8, right?
Yeah.
How can we prove that all of them are less than 8? Or 8 cubed is the best one?
Induction, maybe?
Maybe. So if we focus on this, for example, f of x is x plus 1 over cube root of 2x, right?
Yeah.
Maybe induction, maybe differentiate, right?
Yeah.
Okay, so when you add 1, you are multiplying. So f of x plus 1, what happens? We say this one plus 1, this one times what?
Times cube root of 2.
Yes, or that's right. Cube root of 2. So you add plus 1 in the numerator and multiply this. So it is what? It is, for example, a over b. Then you want to check it with this b, this one, right?
Yeah.
And we want to see under what case it is less than this one, right?
Yeah.
Here we can cancel b. It's equivalent that a cube root of 2 minus 1 is less than 1, right? So a is less
Yeah.
than 1 over cube root of 2 minus 1, right?
Yeah.
So it would be what? It would be cube root of 4 plus cube root of 2 plus 1, right?
Yeah.
So this one is less than what?
That's less than.
Maybe we can say it's less than 5, right?
Yeah.
So if a is greater than 5, greater than equal 5, it is decreasing,
Yeah.
right? So, for example, if you can check at most until 2 to the 5, right?
Yeah.
And in general, if you want to check it with a over b less than a plus 1 b cube root of p, then again we can say same thing, right? A cube root
Yeah.
of p minus 1 is less than 1. So
Okay.
a is less than 1 over cube root of p minus 1, right?
Yeah.
Which is cube root of p squared plus cube root of p, right?
Yeah.
And plus 1. If it is less than this, it is increasing. If it is greater than this, it is decreasing, right?
Yeah.
So we understood that if a is less than this, it is increasing, right?
Yes.
So, for example, how can we make sure that we should check until which prime?
If the value starts to be less than 1, then it's not good.
Okay, 3, let's see. 2 over cube root of 3, right?
Yeah.
It's greater than 1 or less than 1?
Greater than.
Yes. 2 over cube root of 5. It's greater than
Also.
1, right?
Yeah.
2 over cube root of 7, because it's cube root of 8. And 11 is
Yeah.
2
11's
over,
not
this
good.
one is less than 1. So, for all of them, for example, if p is greater than 11, we want to prove if p is greater than equal to 11, we want to prove alpha plus 1 over cube root of p to the alpha. We want to prove it is less than 1, right?
Yeah.
So try to prove this, that y for p greater than equal to 11, this is less than 1, okay?
Can I have a hint?
Okay, sure. So here in the beginning, we know for alpha 1 it's correct, right? 2 over
Yeah.
cube root of p. We want to prove it's less than 1, which is equivalent that 2 is less than cube root of p, which is equivalent that 8 is less than p, and because p is at least 11, it's correct, right? This, right? Agree?
Yes. Yeah.
Okay, so look, if we simplify this equivalent that p is greater than 8, we said p is at least 11, right?
Yeah.
Okay, and when we change alpha to alpha plus 1, let's see what happens. Alpha plus 1 to p to the alpha cubed times cube root of p, right?
Yeah.
We want to prove y is less than 1. So we add the numerator by plus 1 and the denominator by multiplied by this, right?
Yeah.
So it is equivalent to what? Alpha plus 1 y is less than cube root of this one times this, right?
Yeah.
We know alpha, by using induction, we know alpha plus 1 is less than cube root of p alpha, right?
Yeah.
So left hand side, if you consider, is added by 1, right?
Yes.
But right hand side, here, if we consider right hand side, we multiply it by cube root of p, right? Cube root of
Yes.
p is at least what? Is at least cube
2.
root of 11, which is 2, right?
Yeah.
It is greater than 2. And this one also is greater than 2, right? It's cube
Yeah.
root of 11. So when you multiply by this, do you agree? It's no. This one is greater than p alpha cube times 2. So we can say this one. Agree this?
Yes.
Do you agree it's greater than p to the alpha cube plus 1?
Yeah.
So do you agree also we can say plus? So it is greater than by induction alpha plus 1 plus 2. So we prove, right?
Yeah.
Okay, by induction we prove this. So you need to only check until P7, right? 2, 3, 5,
Yeah.
7. But for each of them, we should find the maximum power. So for the next part, we can say P is greater than 2, less than 7. And you want to find maximum of alpha plus 1 over cube root of p to the alpha, right?
Yeah.
So you want to say for 2, for 3, for 5, for 7, alpha is what for each of them?
Mm,
Have you found for
oh,
each of them
so
best power is what?
yeah, for 2 it's 3, 3 it's 2, for 5 it's 2, 7 it's 1.
Okay, so try to prove it. Maybe you can use induction like this. Maybe you can use functions. Try to
Okay.
prove, for example, y for 2 the best power is 3, y for 3 t. Okay, try.
Okay. Okay, I think I proved it.
Okay, can you explain?
Yeah, so you can start with alpha plus 1 over cube root of p to the alpha and say we have a different exponent called beta. So greater than beta over cube root of p to the b. I mean, cube p
Yes.
to the beta. And then you will cross multiply and simplify, and
Let
eventually
me
you'll
check. Let
get,
me check. You want to say, okay, if it is not maximum, there exists another maximum that the power is beta. You meant this?
yes,
So beta plus 1 over p to the beta. Cube root of
yes,
this is greater than alpha plus 1 for each of them. And cube
yeah.
root of p to the alpha. Then what?
So you expand, but you don't expand alpha plus 1 or beta plus 1. So you treat that as just one number. And then
Ah,
eventually you'll get,
alpha plus 1 like this over beta plus 1 is
uh,
greater than. You
yes,
can consider beta is greater than alpha, right? Because checking
yeah,
x before that is easier. So p to the alpha, p to the beta. So it would be 1 over p to the beta minus alpha cube root.
yeah.
Then
So
what?
then from here, cube and then reciprocal.
Uh-huh. So it is equivalent that cube root of p to the beta minus alpha is less than beta plus 1 over alpha plus 1, right?
Yeah.
Then what?
Cube.
On. So p to the beta minus alpha is less than beta plus 1 over alpha plus 1 cubed, right?
Yes.
Then what?
And then, so from here, p is a constant, alpha is a constant, and beta is the only one that will change.
Then,
So as beta grows more and more, the left side looks like p to the x, and the right side just looks like x cubed. So the left side should be greater, but in this case it's not. So it's a
yes,
contradiction.
eventually this one will be greater, but maybe, for example, why alpha 5, alpha 6, alpha 7? Why those numbers are not better? Understood what I mean?
Mm, yeah.
Yeah, you can prove eventually if you increase alpha, if you reach beta that is so much large, yes. But for example, why for 4? We want to find a general proof. For AMC, you don't need this, but it's good to know how to prove these things, okay? Because sometimes, especially in full solution exams like JMO, it's useful. So we want to find a way that y for example, 2 alpha 4 5, all those numbers are less than this. Y is the maximum one. For this one, y this one is the maximum. Okay?
Okay.
So by this proof, we won't prove this, right? The thing it understands, right?
Yeah.
Okay, so
Yeah.
something. Try to prove the rest of these as homework. Rest of these, you solve these, but try to prove why these numbers are the best. Okay?
Okay.
And